So in this lecture, we're going to be talking about sulfur nucleophiles. Now we learned about the oxygen nucleophiles, and we also learned about the nitrogen nucleophiles. But here, we're going to be learning about sulfur nucleophiles because they too can act as a nucleophile. So our first discussion, we need to talk about the properties of sulfur, and to do this, I drew out a little snippet of the periodic table. If you recall, we have carbon, and the next has nitrogen, oxygen, fluorine, and then the neon noble gas, right? And remember, in the groups, we're told that they each have their own valence shell, or differing numbers of electrons in their valence shells for every group. So in this group, they have 4 valence electrons, right? So carbon has the 4 around. Nitrogen has 5. And oxygen has 6. What's the importance of this? Remember that to be the most stable, you need to fill your octet. So you have to have a total of 8 electrons sharing, or you just have that. So like fluorine, for example, he already has 7, so he'll share an electron in a covalent bond with someone, or he'll steal an electron from someone in an ionic bond, say, to fill his octet. Oxygen is kind of similar. Oxygen, two pairs of lone pairs will come together to make 4 non-bonding electrons. So we have 4 electrons that are not bonding. Then he has 2 that are able to bond, which means he needs to make 2 bonds to get 2 other electrons from other atoms to fill his octet to the total of 8 that he needs. Hopefully remember this kind of chemistry. It was in Gen Chem 1. Notice right below oxygen is sulfur. Sulfur is much like oxygen, where he has 6 valence electrons. He has 4 non-bonding, and then he has 2 that will come together with other electrons from other atoms to fill his octet to 8. Okay, so oxygen and sulfur are basically the same in their electron distribution. That means they function very, very similarly. The only thing that they really differ in is their size. And that leads to a bunch of different properties. And sulfur also has access to different orbitals, so it can expand its octet and make more than 2 bonds. But for the case of this course, we'll be talking about sulfur making 2 bonds in this case for sulfur nucleophiles. So I hope my point gets across that it's going to act much like oxygen and much like oxygen nucleophiles. In fact, the mechanism is completely synonymous. Okay, so let's go through the reagents that we need. So we go from a carbonyl to what we call a thioacetal, and it's kind of like, if you remember, turning the carbonyl into an acetal using the corresponding alcohol, right? But instead of oxygens, we have sulfurs. Okay? So keep that in mind here. So if we need to use an alcohol to make an acetal from a ketone, how do we make a thioacetal? Well, we use the corresponding thiol for that. So we're going to use RSH, meaning carbon chain, the sulfur, the hydrogen, a thiol, or a mercapto if you're really fancy. And we need to use some sort of acid, so we'll use H2SO4. Okay? So, and you could also use basic conditions, but I'll show the mechanism in acidic mediums. So we start with our carbonyl, and we're going to steal a hydrogen ion. Pretty simple, we just activate the carbonyl. Now it's subject to attack from the acetal. One of his lone pairs is going to reach out, kick up electrons onto the positively charged carbonyl. So now we have an alcohol, and we have our sulfur here. What's going to happen next is we are going to we're going to deprotonate our positively charged sulfur. We could use another equivalent of sulfur here. And we're going to form this nice little molecule. Okay, so this is pretty stable, but what happens next? Well, that oxygen is going to see this little nice juicy proton, and he's going to be like, yep, mine. Pretty simple step. We're just getting a little closer to where we want to be. Notice our water has a positive charge. This allows a nice pesky little sulfur to come in, and he's gonna do backside attack and kick out the water group there. So we're gonna get a protonated thioacetal product, which can just be deprotonated by another thiol. And then our final product is a thioacetal. Now, I went a little fast, so let me summarize what we've done here with this mechanism. So we protonated a carbonyl. Okay, that activates it. That makes this carbon more positive, right? It's going to really feel like I'm unstable. I need someone else, oxygen. You're just not cutting it. So the thiol comes in, slams into the molecule, kicks up electrons to stabilize the OH. Then we need to deprotonate to make our sulfur more stable. And then after that, we have a stable molecule. Then we take an OH, we protonate it, and then we kick it out with backside attack by a thiol. What we're then going to do is we're going to deprotonate that by some basic species. In this case, I picked the thiol again to deprotonate. And then we get a thioacetal. Okay, so now we know how to make thioacetals. And please note, remember how we talked about cyclic acetals? You can make cyclic sulfur nucleophiles. So you could use this equivalent. Hopefully this will be familiar. I'm not going to touch much on it, but it's much like this molecule here, where on a ketone it will react to make kind of a protecting group. Now, I want to point something out about something that you can do with thiols. Remember we looked at Wolff-Kishner reduction or some of the other ways of hydrogenating, right? Or turning a ketone into an alkane, just chopping it off. Well, we could use Wolff-Kishner reduction, but we could also do a different method. So let's say we convert our ketone into an acetal, right? Using the methods just explained. Now what I want to do is use something called Raney nickel. Raney nickel. And that's going to give us an alkene. Or sorry, an alkane. Not an alkene, alkane. Right, so we make a thioacetal, we use Raney nickel, and we get an alkane. So what is Raney nickel? Well, it's an aluminum nickel complex catalyst. And what's going to happen is there's a bunch of hydrogens, and you don't need to know the mechanism for this class, but I'll kind of explain what goes on. And me, myself, I don't really know, but here's the best way I can explain it. So we take nickel, and the nickel, he's a little hungry guy. So he's going to bind to the sulfur. Sorry, I had to kind of go around the R group there. And another molecule of nickel is going to come in and attach itself. So what happens is we're going to get bonding to the catalyst, and then nickel is bound to the sulfur. Then a hydrogen comes in and swaps places with the nickel. And then we get bond formation. And then the same thing happens here, where that nickel comes in, chops off the thioacetal, and replaces it with a hydrogen. So that's how Raney nickel works. That's how it's really synthetically useful if we want to get rid of a ketone. And let's say we don't have a hydrazone to make the hydrazine complex, right? This thing here, with say a Wolff-Kishner reduction. I'm kind of forgetting what it looks like. Anyways, the hydrazone, we make that, and then we can use Wolff-Kishner reduction. KOH, H2O, and we heat it, right? It gets rid of it. So that is all of sulfur nucleophiles. That is all you need to know. It's kind of a short video here, but very important that you know these reactions because they are synthetically useful if, say, like you don't have hydrazone or you need to make a thioacetal, like in, some good applications of this might be in, say, disulfide bridges in proteins. Like this kind of chemistry is important. So hope you have a wonderful day, guys.